So in this second talk, we are going to talk about a generalization of the regularity theory I presented in the first lecture, and then I'll discuss the proof in the more general setting, so which covers the minimal surface case as well. Okay. So first, let's just recall what we heard in the last lecture. So the regularity theory says that in codimension 1, if you have a stationary object, a stationary integral waterfold, and with stable regular part and no classical singularities, and that then the singular set is codimension 7. And so the extension I want to talk about is to sort of essentially looking beyond minimal surfaces now. At the moment, this is sort of work that we finished for the CMC case, but hopefully that can be extended even a little bit more than that. All going to be joint work with Costante Ballatini at UCL. The idea here is, the emphasis here is to get a theory with sharp hypotheses and conclusions sort of saying that the surfaces are classical. So in the CMC case, if you think about it, this is already going to be a bit different, because one important difference in the CMC case as opposed to minimal is that two things can touch. You can have two spheres touching or two cylinders touching, C2 guys in that way. So that actually is the main difference that creates a lot of issues for the proof, this lack of maximum principle, like in the minimal surface case. And then, I'll tell you what the right sort of hypothesis are. It took us a while to actually realize what the right assumptions are. And there are some sort of surprising, easy to write down counterexamples if you drop this hypothesis. Okay. And of course, one can also look beyond minimal surfaces in terms of existence side. What ways can we prescribe the mean curvature of a hypersurface? What sort of functions, ambient functions, can you take as the prescribing functions for the mean curvature? This sort of thing is completely open. This variational theory on that side is actually seems to be widely open. And in the case of prescribed constant mean curvature, you can do kind of old results that tell you that you can construct things with small or large mean curvature near sort of small geodesic balls for large mean curvature, that you can perturb them to CMC, and also you can, under certain assumptions, once you have a minimal surface, you can find something with small constant mean curvature nearby. This sort of thing, these are perturbative results. They are obtained by non-variational methods. Now, recently there is a paper of Zhou and Zhu, which asserts the existence of a closed hypersurface with prescribed constant mean curvature in these dimensions between 2 and 6. This work is following Armgren-Pitts type construction, where you do min-max process for a suitable functional directly on the space of hypersurfaces. So you have to, there's quite a bit of technical challenges in carrying this out. Now, given that we have seen this Alan Kahn alternative, and in a way sort of conceptual simplicity, because you're bringing in a lot of PDE to the problem now. Your min-max construction, as we saw in the last lecture, is entirely at the level of the PDE. For fixed epsilon, you construct a index 1 critical point of the Alan Kahn functional by very standard sort of PDE min-max theorems. And then you pass the limit. So the burden, you shift more to the compactness, convergence, regularity sort of questions. That's sort of the philosophical difference between the two things. And then so it's this very tantalizing, so you can imagine whether you can extend this kind of constructions to beyond minimal surfaces. Okay, but that is a very sort of a fairly long-term goal to get to that. But at the where we are now we've completed a CMC version of the regularity theory. Okay, and this is what I want to describe. So, but I'm going to start with the classical setting. So, remember in the minimal case, all the hypotheses of the theorem. So, the structural condition involves sort of fairly regular structure, and stability is only assumed on the regular part. And we want to preserve those good things when you generalize this theory. In other words, we would like the variational hypothesis to be assumed only on the regular part. Okay. And then come up with suitable, easily checked structural hypotheses that will guarantee the regularity conclusions. So, in fact, that is the case. All the variational conditions, including the first variation condition, will only be on the regular paths. So, because of that, let's just start by discussing for the CMC setting the variational formulation for the problem, constant mean curvature condition. And I'm going to actually restrict to the Euclidean ambient space because mainly for technical simplicity of presenting things, and it involves very little loss of generality, because regularity theory is by nature this is a local theory, and you get, when you go to the Riemannian setting, you get terms, error terms, which are fairly sort of routine to handle. So all the main ideas will already be in the Euclidean ambient setting. So now we're going to discuss the classical setting. So we have a C2 hypersurface M in some open set U of Rn plus 1. And then we have the two functionals associated with that. This is the usual area functional, n-dimensional Hausdorff measure. And then this is meant to be the enclosed volume functional. And indeed, this expression is the enclosed volume if this hypersurface is actually the boundary of an open set. You can just take this divergence of the coordinate vector field, which is n plus 1, integrate this, and then use the divergence theorem. You can write it as a boundary integral. Okay? And now you can use this as a definition of your enclosed volume without M being enclosing anything. Okay? So as long as it's oriented, as long as you have unit norm. And then we will also need to consider this functional here, this J O, which is that AO plus lambda times the volume functional here. So the subscript O will always mean we are localizing to some open set, right, with compact closure. And we will continue to write HM for the mean curvature vector of M. Now, the first thing to look at is first variation. How do you characterize what is the relationship between the fact that the scalar mean curvature is constant, which is this, right? Once you have a unit normal, that is the scalar mean curvature. And then variationally, how that you can write it in two different ways. First is that the hypersurface is stationary for the area, provided the deformations preserve the volume, enclosed volume. And this condition says that without the enclosed volume condition, it's just stationary for the J functional, for arbitrary deformations, compactly supported, but no requirement here of fixed volume. So these are all equivalent, it turns out. This is easy to check, actually, in the classical setting. Okay? So in particular, we will be actually using this condition C. So you see, at the end of the day, if you want to construct prove an existence theorem for a prescribed mean curvature, that is the right thing to do, because this lambda happens to be the one that you can prescribe that's going to be the mean curvature by this characterization. So, I mean, there's a distinction here, right? If you care about finding a CMC hypersurface in a Riemannian manifold, that's easy to do, much easier than the minimal surface case, because you can minimize by fixing a volume in BV. But then you lose control of which mean curvature value is going to attain. It'll attain whatever it wants to attain. So the focus here is to be able to prescribe the mean curvature value. Like I said, there's no existence theory I will be presenting here that we don't know how that's done, but the regularity side is complete. Right. Okay. So then we're going to look at the stability condition, which is same class of variations, volume preserving deformations of the surface, and it translates into a stability inequality exactly like in the minimal case, except now the test functions have to have zero average on the surface. That is the condition that says that your variations are preserving volume. Okay, so that's the classical sort of setting, and now we immediately go to the Varrofold setting. Integral Varrofold, again, as before. Now, before I define stationarity by saying that it means that this side is 0. Remember, this weight measure is just theta times the Hausdorff measure, right? So now we are going to define what it means for this Varrofold to have a mean curvature. Okay. And that means that we have an L1 function, L1 vector field here, HV, which satisfies this, okay, for every smooth vector field X. This vector valued L1 function is called the weak mean curvature. And this is a definition now. If you had a C2 surface, obviously this is true as long as you don't have boundary. This is a fact, with that being the classical mean curvature. But we're going to take this equation as a definition of the mean curvature now. Okay. So it identifies a subclass of integral Varrofolds. Not all integral Varrofolds will have L1 mean curvature, but it gives you a subclass. And then the basic goal is that starting from here, suppose you have a Varrofold with this L1 mean curvature, we want to put in hypotheses which fairly easily check in applications, ultimately guarantee that the thing you have is actually a classical CMC hypersurface. Okay. So the very first thing to realize is that you need to improve the integrability assumption here. L1 is way too weak to give you anything. So you need LP for the mean curvature for some P larger than or equal to n. Otherwise, your support of the Varrofold, it's easy to construct examples where the support actually is the whole space. For instance, you can put in concentric sort of countable number of spheres around rational points in R3, and so which defines a 2 Varrofold, but the support of this measure, because it's around every rational point, will end up being the whole space. And what's lacking in that example is that the mean curvature is not in L. It's not in a sufficiently high integrability. It's not L. P for P larger than 2 in that case, I guess. So we're going to assume that. Then when you assume that, Allard's theory that I described in the minimal surface setting, actually in the same paper, he did it in much more general setting, i.e. in the setting when the mean curvature is LP for P larger than n, strictly larger than n, where he proved that then the same conclusion holds, that there is a regular part then. There is a dense open set of C1 embedded regularity. Okay? And furthermore, the support now is can't do anything crazy like filling up the whole space. It is actually the same thing as the initial rectifiable set you started with up to a set of measure 0. The key here is that you have a monotonicity formula under this assumption for the experts in the audience. That's what gives you this fact that the support is rectifiable and rectifiable. So, and in fact, once it's not only C1, you get C1 1 minus n over p. So this is very much the PDE, the geometric analog of the Coldron-Sigmund theory, that if you have a Laplacian in LP, then you have a function in W2p. So if p is larger than n, you have C1 alpha. Okay. This is the analog. But then this regular part is still only very small. That's the point, right? You don't know, in measure that, in fact, now actually, so now we can, in fact, we know for sure that that in measure the singular set could be very large. There is an example of Brachy which has weak mean curvature in L infinity locally. It's bounded. And the singular set has positive two-dimensional measure. It's a two-dimensional example. So in the minimal surface case, this is an open question, like I said before. So whether the Brachy's example can be improved to mean curvature 0 is an open question. But for bounded, and hence small, by scaling you can make it arbitrarily small, you could get very bad singular set. And the example uses putting in lots of catenodial type sort of necks as building blocks and patching them together. And therefore, it creates a very large amount of second fundamental form, this example, and hence nothing like stability holds. Okay? That's the moral here. Stability is, even though, so eventually I'll tell you the theorem, is we're going to assume stability only on the regular part, potentially very small in measure, but it has a very powerful effect on the whole varfold because it gives you a lot of control of these neck regions. That's the picture that's emerged from all of these things. So the paper of Mena and Kolodzinski, which actually shows that the Brachy's example can be modified to have, for the second fundamental form is in L1, but not in L1 plus epsilon for any epsilon, and this is true for near any point of a set of positive measure. So you can't really get anything like L2 or so let alone stability. Yeah? Okay. So then this is our familiar thing from last lecture. We will still continue to denote by this thing C the classical set of classical singularities, this type of things. Now we need another definition. Touching singularity, and this means this picture here. It means that the support of the varfold locally at that. So that's this point P is a touching singularity locally in a neighborhood. It is the union of two C1 alpha graphs, embedded C1 alpha graphs touching at that point, possibly also at other points. But the point is that C1 alpha is, you're allowed to assume C1 alpha regularity in these definitions of singularities, right? Both classical singularities and the touching singularities. There's nothing mysterious. They're singular because they're that's not embedded, but it is quite regular. Think about it. You're allowed to assume regularity. So when you check the hypothesis, when you rule out classical singularity, so when you later on control the touching singularity in some way, this works to your advantage. You're allowed to assume they are quite regular. Right. So so let's keep this in mind. Right. These pictures: classical singularities, touching singularities. Now, so this is the Cmc regularity theorem. Joint work with Custon to Bellatini. So integral n varfold in an open set U, and then weak mean curvature is in LP for some p larger than n. And then we have 4 hypotheses, 2 structural hypotheses and 2 variational hypotheses. First one is no classical. So anything to, so of course this theory is going to be meant to be a generalization of minimal surface theory. So we know that we have to rule out classical singularities, right? And about, so this is the one, this is what came as a bit of a surprise to us. This is the subtlety involved in these touching points. The assumption here is that at a touching point, touching singularity, we are saying that locally near there, in some neighborhood, if you look at all other points which have the same density, then that set has n-dimensional measure 0. Okay? This is the second assumption. Right? We have to control. Of course, ruling out touching singularities is included in this, but we're not going to go as strong as that. We're just controlling in measure how big the set is with the same density as the touching density of the touching singularity. Now, the density of the touching singularity need not be 2, because the C1 alpha is for the support, but each, these curves might come with multiplicity, right, in various ways. So the density could be larger than 2. But in that, so you have to check that the set of points where the density is equal to the density of the touching point. That set is Hn null. And this is necessary. I'll give you an counterexample in a minute. And then we have the usual variational assumptions, stationarity and stability. Stationarity for the J functional, yeah. Stability for on the C2. There's a slight change here from the minimal case. We're going to assume stability on the C2 immersed part. Okay. See, before I was only assuming in the minimal case C2 embedded part. So the difference between immersed in this setting, immersed means that you're allowing touching to happen. But you're not allowing crossings to happen because you've already ruled out classical singularities. Right? You're not allowing sheets to cross transversely, but you're keeping the possibility in the conclusion that they can touch. So stability as an immersion means that you're allowed to vary independently these sheets. So then the conclusion is exactly the same as in the minimal case. Well, okay, so not quite, but the genuine singular set is codimension 7. And any other, so away from that set, which is a closed set, the picture, local picture is either the support is an embedded graph, it's an embedded disk, or 2 embedded disks touching. They are both C2 and hence analytic in the Euclidean space. All the higher regularity conclusions follow. And then the mean curvature is given by, it's a constant, scalar mean curvature is this lambda that's you prescribed here. Okay, the functional is defined. And then once you know that, because everything is C2 and in fact analytic in this case of ambient analytic metric, it's easy to see that this touching can happen only along an n-1 dimensional set at most. That you can say more about the touching set. Okay, so the examples that show that these are necessary assumptions. For the classical singularities, clearly you can take two spheres crossing, pieces of spheres or cylinders. And here's the more interesting one, the assumption 2, which says that the touching set has to be, not just the touching set, all the points near touching set with the same density, this has to be controlled. If you drop that, what can happen is that you don't get C2 regularity conclusion. So here's the example. So this is a one-dimensional example in R2. So piece of a circle, and then that's a circle. There's a unit radius, everything. So constant curvature. And you give density is 2 here, 1 and 1. So this actually is a critical point for the J functional. It's easy to check. And it is stable in the immersed part, meaning that away from the singular point, it's graphical, right? So it's stable. No problem. So the only assumption that's not satisfied by this example is this assumption B about the touching singularity. See, if you think about this, the set of points where so the touching point has a density 2 and has density 2 here, this singularity, And also there's a set of positive measure of density too here on this side. And the conclusion fails in the way that this is not union of two C2 graphs, but it's a C2 graph and a C11 graph. Okay. So the best hope if you drop assumption B is to prove that you get C11 conclusions, not C2. So again, this is just emphasizing what I said before. All the assumptions, except for the fact that the mean curvature is LP. That is the one that sort of goes across the singular set. That's the one connects everything and gives you monotonicity formula. If you think about the proof techniques that you get started with, and all the other assumptions are actually on the regular part. Nice, you're allowed to assume some, C1 alpha regularity at least. Right. So this, So then we get useful corollary for Kacher-Poli sets. These are the boundaries. If you think of them as boundaries of open sets, for instance. These are the sets for which the divergence theorem holds, with respect to some measure. And there now you have a natural notion of enclosed volume, which is the volume of the set. It's a boundary of something. So the J functional looks like that. Boundary measure, and then lambda times the enclosed measure, n plus one dimensional measure of the enclosed region. And so the corollary says that we still have to obviously rule out classical singularities. And then there's nothing about touching singularities. That's what the corollary involves. A, C, D, there's no B. And C and D are stationary and stability assumptions. And then you get the same conclusions. And the reason why this follows from the theorem is because by de Giorgi's structure theory for Kacher-Poli sets, automatically de Giorgi proved that these are rectifiable, these Kacher-Poli sets. So they have almost everywhere, they have a multiplicity 1 tangent plane. And that means any other thing that away from that is a set of measures 0. So that means that the hypothesis B here is automatically satisfied. See, n-dimensional measure. This is the reason why we wanted to prove this theorem in this generality. So the proof of the theorem, actually, if you assume, say, n-1 measures 0 here or something like that, it is actually becomes a lot closer to the minimal surface case then. You only need sort of technical modifications. But because we have this only that the n-dimensional measure 0, which is compatible with de Giorgi's structure theory, this is really the motivation for that assumption, it gets more sort of trickier. And the Kacher-Poli sets is a natural setting for CMC, in fact, right? If you think about kind of the Alan Kahn approach to this, you can imagine that this phase separation will give you something which is, if there is a phase separation actually in the Alan Kahn process, always the surface comes as a boundary of one phase, right? So, so the corollary is what one would expect to be useful for the existence sort of thing. And the theorem, the proof of the theorem, so the corollary is not a lot easier to prove. So it's it's really the same. See, the point is that even though you have multiplicity 1 almost everywhere, if you take a tangent cone to a Kacher-Poli set, that could have multiplicity higher than 1. So a priori, you have to deal with higher multiplicity, even in this setting. Okay, so that's why there's not much difference between proving the corollary and proving the theorem. It's really amount of work is essentially the same. And then we also get a compactness theorem for this class. Once you have a uniform area bound and uniform bound on the mean curvature, and satisfying all the hypotheses as in the regularity theorem. Let's see. Well, I think so there should be a mean curvature bound somewhere here. So the theorem will give you mean curvature is constant, right? But I should, there's a hypothesis missing here. So the area bound plus you need the mean curvature bound. You need to control the mean curvature. Otherwise, you can have little spheres sort of contracting. So. Okay, so moving on. So let me now, for the remainder, discuss some proof ideas involved in this setting. So as I said, I'm going to discuss in this generality, but I'll point out where the differences are from the minimal surface cases versus this general case. So the first thing to observe is that you can assume strong stability rather than, so the stability condition for CMC is that the test functions you are allowed to plug into this has to have 0 average on the surface. And this is a condition you assume on the smooth part. So the second fundamental form is all classical, smooth, immersed part, right? Which we call the generalized regular set. That means that the embedded part and C2 touching part. Okay, C2 is assumed here when you check the stability. So then the first thing to realize is that you can by coming into a very small neighborhood around a point, you can check that the strong stability holds, because the point is that if you have two disjoint open sets, and if the thing is weakly stable, then it must be strongly stable in one of them. Because otherwise, if strong stability fails, that this inequality fails for two test functions which have disjoint supports, then you can cook up a test function with 0 average by combining them and violate the weak stability. So because of that, you can find locally, so the assertion here is that locally the thing is strongly stable. Okay, so we'll assume that in our quantitative estimates that we're going to prove, the strong stability holds. Okay. So now we're in a class of waterfalls which are strongly stable in this sense and also satisfying all these assumptions as before, with a bound on the mean curvature, some bound. Then the goal is to prove, so the regularity statement and the compactness statement I mentioned, these are sort of qualitative versions, right? There are estimates now need to be established, and these come in as sort of three theorems. So the first one is called a Sheathing Theorem, which says that essentially, so the assumption here is that there's a certain quantity which I call E here. This is called the excess for a given waterfall in our class V, which measures, so this bit of the excess measures how far it is from a plane in L2 sense. Okay, from Rn, this is how far it is, and then there is the mean curvature term, LP norm of the mean curvature term here. We want both of them to be small. That's what this implies. Okay, and we also have uniform volume bounds from above and below by some integer q. So q might be volume in the cylinder of the inside the cylinder is between q minus a half and q plus a half, okay, for some integer q. And then the conclusion is that in the interior, in the half ball, this waterfall decomposes into nice graphs. So this theorem rules out this behavior, this neck behavior. Okay, that's the point of the theorem, to rule out necks. So we have q graphs, ordered, we are in codimension 1, these are ordered U1 through UQ, C1 alpha graphs to begin with for some alpha, less than a half, it turns out that's the best you can get in the first iteration of the theorem. And so there you go. So that's the conclusion. The thing, the geometric content is that you're knocking out this kind of bad sort of neck behavior, like a catenoid type example can't happen. As soon as it's close to a plane, they're ruled out. And see, the sheathing theorems are sort of well known. This actually goes back to de Giorgi, in fact, in the area minimizing hypersurface case. That's the fundamental discovery that de Giorgi made, was that you can prove this sort of sheathing theorems by approximating the surface by graph of harmonic function. So here you would do, and in Schoen-Simon you have the same sort of thing, approximating by several harmonic functions. And so the same general idea is what's used to prove this theorem, approximating by graphs of Q graphs of harmonic functions, ordered under these assumptions. Now, what's different in this setting is that, see, in the previous theorem, so once you have this sort of sheathing theorems, you can start from there and control all other sort of bad singularities. So a sheathing theorem would rule out a singularity at which there is a multiplicity 2 tangent plane, for instance, right? Because if you have a multiplicity 2 tangent plane, then after you rescale the Varrofold, it gets very close in L2, even in Hausdorff distance, to the plane. So the hypothesis will be satisfied, and the mean curvature term, because it's in LP, that's going to become small and small as you rescale. That's the point about P being larger than N, right? It decays. So this will be satisfied near any point where there's a higher multiplicity tangent plane, and the theorem would tell you that before you pass the limit, the surface has to be smooth graphs. Yeah. So you couldn't have had a singularity. The whole surface must have been Q times a single embedded surface. That's how you use. So then once you have that, in previous sort of versions of this, in Schoen-Simon or so on, that an area minimizing hypersurface case before that, you can knock out all the other singularities by this. This is a sort of well-known principle called dimension reduction. Would carry we can do that. In particular, you can rule out tangent cones which are half planes meeting along an axis once you have a sheathing theorem. But the difference is that here you can't quite prove a sheathing theorem independently. So that's the twist here. To prove the sheathing theorem, you also have to incorporate a theorem that rules out tangent cones which are half planes meeting along an axis, all at the same time. And that's the content of this second theorem, minimum distance theorem. It says that the minimum distance theorem says that if you start with a cone like this, it's a minimal cone now, right? Because CMC thinks once you take tangent cones, they are minimal cones. Mean curvature goes away. So if your Varrofold is close, so the minimum distance theorem says that your Varrofold in your class cannot be too close to a picture like this in a ball, in the unit ball. There is a minimum distance between, so the Varrofold has to lie outside of some neighborhood. That size of the neighborhood depends on the cone, but that is sufficient to rule out tangent cones of this type. Okay? Because if a tangent cone happens, then obviously the whole surface will converge to this. Right? And then we have a third theorem, which is the higher regularity theorem. Now, normally this is a triviality in P. This is a PDE consequence. For minimal surfaces, this is the case. But under these assumptions in this setting of CMC, especially with that touching set assumption being only that n-dimensional measure is control of the density, this is actually non-trivial. And the theorem says that once you have C1 alpha graphs already in the setting of the conclusion of the sheathing theorem, they are C2 and higher regular. That's really what it is saying. That statement is true for the support of the Varrofold. Okay? And then once you have that, then every sheet solves the CMC equation and all the higher regularity follows. So as I said, in previous settings, proving the sheathing theorem is what you do first, and you do it independently, and then use that to prove, and higher regularity in the minimal sort of case is immediate once you have C1 alpha. And this minimum distance type thing, ruling out this kind of tangent cone, is actually a consequence of a sheathing theorem. But the dilemma, so the sort of difficulty here is that you can't really prove a sheathing theorem without a stability inequality. I mean, we do have a stability inequality, but potentially on a very small set. The regular set is potentially very small. Right? In Chern-Simon, singular set is already assumed. This is the reason why they had to assume that, or the way they used the smallness assumption on the singular set is to say that once stability is true on the regular part, and the singular set is very small, stability ignores the singular set. It's removable for the singular. But under these assumptions, potentially the singular set could be even positive n-dimensional measure a priori. No such thing can be made a priori. No such claim can be checked a priori. So you can't really find it. It's a good way to use stability directly for this. And that's why you got to, so the thing that ultimately works is that you prove all these theorems at the same time. Okay. So kind of the bit of a philosophy emerging from this is that if you can't do one thing at a time, then just do them all at the same time, and that works. I'll come to that maybe a little bit later on, explain why exactly. It seems to be sort of a necessary approach, actually. Right. So this high regularity, I already said that this is a bit tricky to do in the CMC case. That's the main difference between the minimal case and of the theorem and the CMC case. And then this slide explains, once you have those two theorems, Sheathing theorem and the minimum distance theorem and the high regularity theorem, ruling out, so Sheathing theorem would rule out tangent cones which are planar, minimum distance theorem rule out tangent cones which are half planes meeting along an axis, and then you can proceed by dimension reduction, this so-called dimension reduction, which takes over, and this is a standard argument. You take tangent cones and look at their singularities away from the origin, and you take another tangent cone there, and then apply the theorems repeatedly to control the whole singular set until you get down to codimension 7. So the spine dimension of the thing that is standard once you have minimum distance theorem and the Sheathing theorem is that you can show that every tangent cone at a singular point, I mean non-immersed point, that's what I mean here, singular, it has to have the translation invariant directions of the cone has to be at most dimension n minus 7. Yeah.
Momentarily confused about when you have two spheres touching each other, the mean curvature vectors are pointing in opposite directions.
Yes.
So if you have more,
you can't have more.
Yeah, exactly.
That's right.
Feels like, so you have this sort of layer of
right.
things.
Well, yeah, I'm glad you asked this question, because I remember in the assumption, this touching set assumption, I only defined a touching singularity with just two sheets. The reason is precisely you can't. That's all you need for the reason you mentioned. You can't have three things coming together if you know there's C2 already. See, but this is only C1 alpha in the definition of touching set. But the theorems will improve it to C2 first, and then you know that's true. Right. Yeah, you have these conclusions which say that you have Q sheets, but they only touch pairwise. So you can have
These inequalities, but they sort of touch at different places.
at different places. That's right, different places. Yeah. So then the general principle of Armgren says that once you control the spine dimension of the singulars of tangent cones, then that automatically gives you the complete control of the dimension of the actual singular set. Okay. That's all sort of standard geometric measure theory tools. And so the proofs, as I said, is all three theorems all at the same time, inductively. And the sheathing theorem induction parameter is the number of sheets. So this is Q. Minimum distance theorem, the induction parameter is the density of the cone, which is in this set. It's either an integer or integer plus half. And then for the higher regularity theorem, again, the induction parameter is the number of sheets. And then the way that you complete induction is that you prove the sheathing theorem first, i.e. as stated. So you assume it's true for Q minus 1 up to Q minus 1. Complete the induction for the case Q, which essentially, in a very essential way, uses both these theorems inductively to prove that. And then once you have that, it's important to do this in this order. Then once you have that, you use that to prove the minimum distance theorem for the density Q plus a half, then use both of them to prove the minimum distance theorem for the density Q plus 1, and then you prove the high regularity theorem. And throughout this proof, there's a lot of geometric measure theory tools that were developed in the past are used. So quite a heavy, large number of things coming from different directions, and particularly use Leon Simon's work on asymptotics for singularities for multiplicity 1 class minimal surfaces, which he did in the mid-90s. See, you would have to see, if you think about the minimum distance theorem, for instance, the assumption is that you're ruling out a certain type of singularity, this type of singularities. So in the proof, you expect somewhere to be able to create one of these things to get a contradiction. Right? So, because it's a structural condition, you need to find a way under these sort of contradiction assumptions to actually produce in the Varfold a singularity which is a classical singularity, which is the whole structure has to be this classical structure. And that's where the Leon's estimates come in. To do that, you have to modify. These were done in multiplicity 1 assumptions, but it turns out under the inductive assumptions, these contradiction assumptions, you can actually extend that to higher multiplicity setting, these estimates. And the other key tool is that we depend heavily on the Shane-Simon version of the theorem, i.e. that once you have control on this singular set, you have estimates. Right? We do use that at a number of places in the proof. So philosophically, this is a proof where once you know estimates for smooth things, you remove the smoothness as assumption. You can think of it that way. Sort of a fairly familiar concept in PDE somehow. Estimates sort of imply regularity, that sort of thing. Okay, so this is my final remark. So I sort of alluded to this before. So the point is that, let me just describe this. To prove the sheathing theorem, which says that when the Varfold is close to a plane, sort of sitting here, you want to say that. So this conclusion, a priori, this picture is ruled out, right? The sheathing theorem says you have nice sheets like this, and see, this is density Q, this plane. And if there are points of density Q on the Varfold, you can use the monotonicity formula in a very good way, it turns out. So the problem region is actually when you have density less than Q, but you're still close to Q, multiplicity Q plane. So then your enemy is something like a catenoid, right? It's all density 1, but you're getting close to a density 2 plane. So this is where you would really badly need some sort of stability assumption to knock it out. But you can't use stability because there's a large singular set. So you've got to control the singular set by a dimension reduction argument. That's why you need inductively assume the minimum distance theorem. So to prove the sheathing theorem, you need a minimum distance theorem. On the other hand, to prove the minimum distance theorem, which says that you can't have a Varfold coming close to this, at least away from this axis, you need to be able to get good control here. It would be nice to have that away from this here, this region, if the waterfall is close to this picture, then it breaks up into nice pieces, nice smooth graphs. So something like a sheathing theorem is sort of the starting point for that as well, to get a contradiction. So to prove the minimum distance theorem, you need the sheathing theorem. And that's why you do it inductively. You prove both of them at the same time. I think that's it. Thank you. Well, you can, so the non-negativity of second variation makes sense across the singularities, but the assumption is weaker. We only move, when you check stability, you only move the regular part. So if you happen to know it's, second variation non-negative across the singular set, great, that's fine, but it is a weaker assumption. And in fact, as far as I know, that the only way to use stability is to actually do it, use it on the regular part, where the second fundamental form has a meaning. The topology, no, that's a good, Allen-Kahn method doesn't seem to give, but it is, right, I think Allen-Kahn method somehow needs to be explored further. This is sort of still the sort of beginning, but as far as I know, topology, controlling topology doesn't seem to be very promising, actually.